Gracias. So today I'd like to give you a little presentation about what we call the groundwater replenishment system, our project that we're using to try to address an ongoing several-year drought in Southern California, as well as issues we have with water availability that were used in the past. First, I'll give you a little bit of background about the Orange County Water District. Orange County Water District is formed in 1933. It's formed by the government of California as what we call a special district. So in the United States, especially in California, special districts are created just for a sole purpose of addressing a particular need. In our case, the Orange County Water District was created solely to manage the underground aquifer that underlies our service area. And the map you see here is our service area with, this is all of Orange County. The colored portions on the map are all the different retailers, or what we call public retailers that supply drinking water. The black outline is the border, that is our service area. Our service area underlies the underground aquifer itself, and you can see how our service area doesn't cover the entire county or the entire jurisdictional district, because once you go south of our service area, there isn't appreciable groundwater. That's where the groundwater ends. So we have about 2.5 million people in our service area who rely on groundwater as their primary drinking water source. So because the Orange County Water District is a special district or government agency, we are governed by a publicly elected board of directors. This 10-person board of directors, elected officials, politicians that run the Orange County Water District. And their main job each year is to determine the cost of the groundwater, to approve the cost of the groundwater, which is our main income source, our source of funding for all of our projects, as well as to determine how much water can be pumped from the groundwater to supply drinking water needs. And that's a term we call basin production percentage. So each year, through a scientific survey with our geologists, we determine how much water is allowed to be pumped from our groundwater basin to avoid overdraft and to make sure that the groundwater is sustainable. We have had periods in the past droughts where pumping of groundwater has not been managed as closely, and we've had overdraft. Currently, we do have some overdraft, but it's this management that allows this groundwater to be sustainable and forces the drinking water retailers or the people using drinking water to manage and conserve correctly the amount of drinking water they use from groundwater, because we have to limit the amount of pumping to avoid overdraft or subsidence or other issues associated with overuse of groundwater, which is common in other parts of California. So we have several different facilities that we use to manage the groundwater itself. The groundwater basin itself, or the aquifer, is basically replenished by three main sources. The main sources are including what we call the Santa Ana River. This is a local river that the Orange County Water District has rights to. This river is heavily influenced by tertiary effluent or treated wastewater discharges. We also receive water from outside of California, or imported water that we manage, as well as advanced treated or recycled water that we'll talk about today as part of our groundwater replenishment system. And then, of course, the Orange County Water District does operate several facilities that are put in place just to divert Santa Ana River water and our imported water supplies into large holding ponds or lakes, spreading basins, in order to replenish the groundwater. And all of the water quality that's measured, including from the aquifer itself and the water leaving the groundwater replenishment system treatment plant, is all being analyzed by our, what we call our Advanced Water Quality Assurance Laboratory. So the Orange County Water District does all of its own water quality monitoring and analysis. So you may have seen some photos like this of other groundwater basins. This is a cutaway or cross-section of our groundwater basin, where from the left is the coast and from the right is about 30 kilometers inland. When you look at it, you can see that our groundwater basin is quite large, but it's also not continuous. It has several layers, and there's three main layers that we worry about. There's the principal aquifer, where most of the water is withdrawn or pumped for drinking water. There's a deep aquifer, which is the part that most of the retailers don't pump from because the water has got issues with color. And then we have the shallow groundwater, which is where we replenish from, and also the area where we have some pockets of saline or brackish groundwater. And then along the coast, you can see represented by the darker color, we do have seawater intrusion, which has been an issue for us since the 1960s. For almost 60 years, we've had issues with seawater intrusion, and that's driven by large coastal pumping or over pumping along the coastal area where the population centers are the greatest, and that results in water dropping below seawater level. And so to address that, we've had a system in place for about 40 years to address seawater intrusion, and this is a common problem in a lot of Southern California groundwater basins. So one of the issues that we have, which is similar to some of the issues here in this part of Spain, is that we have a very little rainfall that naturally occurs. And we've been, as I mentioned earlier, in a severe drought for several years ongoing, 5 to 6 years. It's been a pretty drastic drought. And you can see that our normal precipitation is about 330 millimeters, and we've had significantly less than that, especially in 2013, where it was a third of that at 91 millimeters. And without that natural precipitation, not only does it limit the amount of flows we have in our Santa Ana River, our local river that we use to replenish the groundwater aquifer, it also limits the amount of imported water, or water that we can purchase from outside of Southern California to also use to replenish the groundwater basin. So all of these issues coming together leads to not only a scarcity of water, it leads to an issue of how to better manage groundwater to sustain the population growth. So if you look at the two major sources that I mentioned before, this gives you a little schematic of what they are and what their cost is. The picture on the left you can see is the imported water that comes from outside of Southern California through a local agency called Metropolitan Water District. So this is imported water from the Colorado River or from Northern California that can cost, typically around 80 cents a cubic meter versus water that we can produce on site at the Orange County Water District. The groundwater itself, which costs about 33 cents US a cubic meter. So the cost of groundwater is still quite low because the sources that we use to replenish the groundwater, especially the Santa Ana River water, are virtually free to us. And then some of the other sources that cost more, the costs are kind of subsidized and melded together into one groundwater basin so that we can charge the price for groundwater is still quite reasonable. But we do, like I said before, have to manage the amount of groundwater that we allow to be pumped to avoid overdraft. So as I mentioned before, the main sources of water that we try to concentrate on is the Santa Ana River, which contains quite a bit of what we call tertiary effluent or treated wastewater, water that's been treated to a high level enough to be disposed of in local rivers or the ocean. We have what we call the Colorado River or the State Water Project. That's the imported water sources that can be significantly more expensive, but are other sources of water. And then we do have some local rainwater, and we try to capture some runoff, or what we call urban runoff. And then what we'll talk about today is advanced treated recycled water, recycled wastewater that goes through an advanced process, including reverse osmosis. So this pie chart shows what makes up the main sources in our groundwater aquifer. You can see that our groundwater aquifer typically yields about 425 cubic hectometers per year. So this is the amount of water that's withdrawn each year. And these are the different sources that we use to replenish the groundwater basin. You can see that the blue portion, the portion at the top left, is the imported water source. And then you can see the green portion is what we call the Santa Ana River, the local river water, which is also declining in volume and capacity due to the drought. So our hope is that we can increase the red portion, which is the recycled water portion, using the advanced treated, reverse osmosis treated recycled water, and increase the red portion to help mitigate the fact that the green portion, which is the local river water and the blue portion, the imported water, are both decreasing with the ongoing drought. So what we're hoping to do is maintain or close to maintain the current amount of production from the groundwater basin, even with not only the ongoing drought and decreasing external sources, but also with the conservation in place. We think that we can continue to sustain the groundwater basin, but using recycled water is a key component to maintaining the current usage. So the reason that we're able to go into the groundwater replenishment system project we have today is that we have some history using recycled water, especially advanced treated recycled water. So the earliest form of this is a facility that's called Water Factory 21. It operated in 1976 and was decommissioned in 2003. This is very similar to the treatment facility we have today, except that it used more of a conventional drinking water treatment process, physical chemistry, settling with lime clarification and sand filtration, but it did have a small component, about 19,000 cubic meters a day of reverse osmosis, which was the first of its kind to use reverse osmosis on a municipal or large scale for wastewater treatment. And this was used mainly as a salinity reduction step. And this facility operated mainly to supply water to the seawater intrusion barriers. So all of the production from this facility was injected underground near the coast to prevent seawater intrusion. The Orange County Water District also operates what we call the Green Acres Project, and that's been in operation since 1991. This is a non-potable reuse project where we produce treated wastewater, recycled water that's used for irrigation, mostly for golf courses and fields and some agriculture that's still left in our area. And then what we have that we're going to focus on today is the groundwater replenishment system, which has been in operation since 2008. And its main component here is to not only replenish the groundwater basin, but also improve the amount of seawater intrusion barrier flows that we've had, and to replace the flows that were once supplied by the legacy facility, the Water Factory 21. So in order to make this project a possibility, there was a partnership that was developed, and this is what makes the project unique, is the partnership that was developed between two very large government agencies in Southern California. So the project that we're going to talk about today is the groundwater replenishment system, or what we commonly refer to as GWRS. So this facility produces 378,000 cubic meters per year of highly treated, ultra-pure recycled water. And this facility has been in operation since 2008, and it was recently expanded in 2015. So when the project was first developed, it had expansion capability built into the design to be able to expand the facility at 2 different times. So we've done the first expansion, and we're planning for an ultimate or final expansion in the upcoming years. So this is what's considered the largest indirect potable reuse facility in the world, or a facility where treated wastewater is used to indirectly augment the drinking water supply. And we say that with this facility, we have about enough water to feed about 850,000 people is what this facility can produce daily. So the two large government agencies involved with the planning and the implementation of the project are the Orange County Water District, which I mentioned before is a special district to manage the groundwater basin. And then we have what's called the Orange County Sanitation District. This is also a special district, and it was set up to be the main facility to collect, treat, and dispose of all of the sewage waste or wastewater in our service area. And we both operate in roughly the same service area, so we both have the same customer base, and that's important. By us having the same customer base, the projects that we implement and the rates that we offer them for treating wastewater, us for groundwater, affect the same population. So the question often gets asked, why did the two agencies partner up in the first place? So the main reason is the Orange County Sanitation District operates 2 very large wastewater treatment facilities, and the water that is treated is disposed of in the Pacific Ocean through an ocean outfall pipeline. In the early mid 1990s, about 25 years ago, the Orange County Sanitation District determined that their future flows would increase and that the ocean outfall pipeline would not have enough capacity to meet future needs and future disposal needs into the Pacific Ocean. So at that time, the two districts came together and decided to plan a joint project. And at the same time, we were still ongoing a separate drought. This was from in the late 1980s, so 87 to 92. So the Orange County Water District had its need, which was to replace the Water Factory 21, which was an older facility that reached the end of its life. The Water District not only needed to increase the flows into the seawater intrusion barrier, the Water District also needed to seek some additional sources of water to replenish the groundwater basin. And the Sanitation District also had a need for getting rid of more of their treated wastewater. So the partnership allowed both of us to meet each other's needs and affect the same service population. And this long history of partnership goes back to 1973 when we first put into service and started to build the Water Factory 21, or the facility that was the predecessor to the facility I'll talk about today. And like I mentioned before, we serve around the same, about 2.5 million people in the same service area. And our partnership has always been such that not only do they supply us the treated wastewater for free, they take all of our residual streams for free. And that's part of the partnership that makes the economics of the project feasible. So one of the other things that the reason we came together was not only do we meet Orange County's need for disposal of the treated wastewater, it also meets our need to find an additional alternative source of replenishment for the groundwater aquifer. And since we both have a financial investment in the project, it affects the same service population while meeting both agencies' needs. So the other component that makes the partnership unique is that the Orange County Sanitation also does what's called enhanced source control, and that's important as well. So this is the treatment train that the groundwater replenishment system follows. This is somewhat conventional in what is being done in some facilities in Southern California, where we have microfiltration followed by reverse osmosis, followed by ultraviolet light and hydrogen peroxide, or an oxidative process for further organics removal. And then there's post-treatment, and then the final water after it's been through post-treatment to bring the alkalinity and the corrosivity up to mitigate those concerns. About 1/3 of the water is injected along the coast to prevent seawater intrusion, and then the other 2/3 is sent to our spreading grounds and basically pumped from the treatment facility to about 30 kilometers away to a spreading basin or a pond where the water is allowed to replenish the groundwater basin. So the first major treatment step is the microfiltration. You can see this is sized for about 545,000 cubic meters per day. This is what we call a submerged or vacuum-driven microfilter. We mainly rely upon this treatment process to remove the bacteria and the solids or the suspended solids and reduce the turbidity going into the reverse osmosis process. The reverse osmosis is the workhorse, or kind of the main treatment step. We rely upon this not only for inorganics removal, but more importantly for organics removal. We have to meet a very strict total organic limit of 0.5 milligrams per liter, or 0.5 ppm. And because we have microfiltration as a pre-treatment, we're able to operate at relatively low pressure, 10 to 14 bar, which makes the operating costs a little more reasonable here. And we operate about 85% recovery. So we have about a 15% loss through the reverse osmosis process as a concentrate or brine that gets sent to the Orange County Sanitation District for ocean disposal. And then the final treatment step is what we call the advanced oxidation. So we use high amounts of ultraviolet light combined with 3 milligrams per liter of hydrogen peroxide to form an oxidative process. And this is mainly to address low molecular weight organics that can pass through even the reverse osmosis process. And there's a couple of constituents that are regulated in California that we need to meet the regulatory limits using this process. This also provides an additional disinfection barrier beyond the two membrane processes. And then, as I mentioned, all of the water has to go through post-treatment or treatment with calcium hydroxide or lime, quick lime we call hydrated lime, in order to bring the alkalinity and corrosivity of the water to more applicable levels. And so in the next presentation, you'll hear more about this, but there is a regulatory oversight and what we call the Division of Drinking Water that not only sets the criteria that goes into our operating permit, it also sets the water quality criteria we need to meet, as well as some of the physical criteria, such as the travel time of the water that's produced from this facility, and to account for how long it takes this treated wastewater from the facility to reach the nearest production well or become part of a drinking water supply. And then all of that is enforced by a separate governmental agency that we call the Regional Water Quality Control Board. And so between the two regulatory agencies, they set the criteria and monitoring that's required for our project. And again, most of the water quality that we produce are the drinking water quality constituents are what we have to meet or beyond for most of our permit requirements. So you see here that there's on a quarterly basis, basically 4 times a year, we have to produce a formal report that we submit to the state of California. And in there, we test for over 400 different constituents in the final product water, or the water that leaves the facility after this level of treatment. And it meets a range of different types of constituents: organics, inorganics, volatiles. It also includes some emerging contaminants, contaminants that, like pharmaceuticals that aren't, and personal care products that aren't regulated, but the state is trying to build a database or a history of what levels are common in advanced treatment facilities like ours. And so data that we produce helps the state kind of build up an experience on how much of these emerging contaminants might be possible to pass through even this high level of treatment. And luckily, from what we see, most of that, majority of the times, non-detect, even for the emerging contaminants. They tend to be larger in molecular weight and are well removed, not only by the reverse osmosis or followed by the subsequent oxidation. So one of the most important things is the financial investment in the project. So this is a pie chart or a chart summarizing all of the capital costs to date that the Orange County Water District's expended, even with the expansion. And as you see here, the majority of it, $337 million was paid by the Orange County Water District, not only for the original facility, but for the recent expansion that we've completed last year. You'll see that the Orange County Sanitation District put in almost $200 million, and that was an investment they made to defer construction of a second ocean outfall for disposal of their wastewater flows. Instead, the funding that they had in place was invested into our project. And you'll see that because of the nature of the project, we got almost $90 million in state and federal funding. So this is like a grant money or subsidized money from the federal and state government to help subsidize the cost. And so you can see that at our current production capability of about 378,000 cubic meters per day, we've spent to date about a little over $600 million. And we have, and I'll show in another slide, we're planning to spend another $250 million to expand the facility again. So we'll have almost a $1 billion investment in this project between us and the Orange County Sanitation District. So one of the most important things is the unit operating costs, and this goes back to making the economics of the project possible. In order for us to build a project like this, where we're using treated wastewater, highly treated wastewater to help replenish the groundwater, we need to make the cost comparable or better than the other sources, and that includes the imported water, which has been the predominant source of water for Southern California is imported water. And you can see here, as with any facility that uses advanced treatment technology such as reverse osmosis, the energy is kind of the biggest component of the unit costs. And you'll see here the total unit cost is $480 an acre foot, or about 40 cents per cubic meter. For that allows us to produce the water for about half the cost of imported water and slightly above what we charge for the groundwater itself for our customers that pump groundwater for their drinking water supply. This makes the economics of the project very good. And a lot of that has to do with the size of the facility. A lot of other facilities similar to this in California, the unit cost can be double this because we get quite a bit of economy of scale by having such a large project that helps bring the unit cost down quite a bit. So one of the things, as I mentioned before, is that now, because of the ongoing drought, we want to make the facility larger and expand it to its ultimate capacity, or in US units, 130 million gallons per day is the ultimate capacity. So we had the original project that was built and completed in 2008 that produced about 70 million gallons a day, or 265,000 cubic meters per day. We recently expanded the project to produce 378,000 cubic meters per day, and now we have plans to do another expansion will get us to our ultimate capacity, 130 million gallons a day, or about 492,000 cubic meters per day. At that flow rate, this facility will virtually recycle every drop of wastewater in our service area. The only thing that will remain going to the ocean is unreclaimable waste and our waste product, our brine concentrate from the reverse osmosis. So that's our goal, is to recycle all of the wastewater in our service area and use it for groundwater replenishment. However, you can see from this chart that the drought not only has affected traditional drinking water supplies, it's also affected the flow of wastewater. And what you can see here is a chart showing that the top line in the dark blue is the total wastewater flows going to the wastewater treatment plant operated by the Orange County Sanitation District. And as I mentioned before, they operate 2 plants. The line you see in the red color, that's one of their other treatment plants, and then the one in the light blue, or the bottom line, is the treatment plant from which we get our flows currently. And you'll see that all of the flows have dropped. They have started to divert some of the wastewater to the first wastewater treatment plant, the one shown in the light blue, in order to bring us more flow. But you see that the flows have steadily dropped for 2 reasons. Not only because of the drought, but we've had an economic downturn in Southern California that started in 2008. And the drop in wastewater flows coincided very closely not only with that economic downturn, but has gotten severely worse with the ongoing drought. But we still think there's enough treated wastewater being produced to allow us to go to our ultimate expansion. However, in order for us to go to our ultimate expansion, we would be pulling wastewater from a completely different facility located about 8 kilometers away. And in order to bring that water, that treated wastewater, to our facility, we have to build not only a pipeline, but a pumping station, as well as expand the existing facility. And you can see the investment that's going to be needed in order to make this happen, which is to bring additional treated wastewater to our facility to allow for our ultimate expansion. And you can see that we hope to have this project completed by about 2023, so about 7 years from now. And that'll cost us an additional $250 million US to do this expansion. And that's what puts our total investment close to $1 billion US for our ultimate capacity, or the ability to produce 130 million gallons a day of ultra pure treated wastewater. If you look at the unit costs, I know the chart might be a little difficult to read, but our current unit cost, which is on the left, is about 47 cents a cubic meter. We think that by adding the additional expansion, that cost alone is about 80 cents a cubic meter. And then when you meld the two together, or apply the proper ratios between the two, we think that we can produce the water still for a very reasonable rate in the middle there. That's between, somewhere between 50 and 80 cents. So somewhere around 60 cents a cubic meter, depending upon how the construction costs go. Still cheaper than imported water. And this is the reason recently that our board of directors approved the recent expansion and the expenditure of the $250 million over the next 7 years to allow this expansion to occur. So one of the key components of the project, probably more important than the technical design of the treatment facility, is to allow for the public outreach, or the public acceptance. there's been a history in California, especially Southern California, of the public not accepting the fact that the treated wastewater would be mixed with the drinking water supply, even indirectly, and having that become part of the drinking water supply. So before and during the project's development, there was a significant public outreach effort that started as early as 1997, and it continues today. So we've even had what we call a public information officer, or the person involved, or the head of our public outreach, tell us that this project isn't an engineering project, it's a public outreach project. If the public outreach isn't successful, the project isn't successful. So this was probably the biggest and the first hurdle that we had to overcome in order to implement the project. And what that was this tremendous public outreach effort that cost millions of dollars, but was sustained not only through design, but through construction, through startup, and it continues today. And a big part of that is outreach and direct contact directly with our customers. And this included thousands of public presentations, not only detailing what the project is, but the need and where does water come from. Most of our constituents don't understand that the water in Southern California, a predominant amount of it comes from outside of Southern California. So we had to show not only what was the need for additional water, where does the traditional water come from, and why would we spend this kind of money or make this type of investment? And so one of the key parts of this outreach was that not all of the engagement with the public and with the politicians and with the regulators was done by staff. No consultants or no hired persons were allowed to do the outreach, and this was a key component. So they were making sure that all of the engineers actually gave the presentations, including myself, and try to teach the engineers not to speak with so much technical, what we call jargon or technical terms, and make it very understandable for the general public and the need for the project. And that resulted in no organized opposition, where other projects similar to this have had public opposition, and one of them in particular in San Diego was actually, the project was put on hold or canceled for a short period because of public opposition. So one of the things that we learned throughout this process, and this is something that can be used by other agencies considering the use of recycled water, is that one of the things you have to do is make the need very clear to the public. Not only the need for the water, but the need of water supply in general. One of the other things is the outreach has to be ongoing. There's a tendency in engineering projects to do outreach up front or during the conceptualization of the project, and then discontinue the outreach once the project's into construction. The outreach has to be ongoing. And then the outreach has to be targeted. You can't reach 2.5 million people or your whole service area in our case. So you have to go after community leaders or people that have the community's respect, as well as the elected officials that are the ones that can support the project and make it successful. And then one of the things that we tried to stress is that the quality of the water produced by this facility is of higher quality than the other sources that we use prior to the project for replenishing the groundwater. That includes imported water and local river water. This water is by far superior in quality. So that was a key component of the outreach message. And then once we found out that we could do the outreach in an effective fashion, what we found was that even people that were at first opposed to the project eventually voiced their support once they learned the components of the project, not only the technical components, but the social components and the economic components. And you'll see here on the bottom, this is a picture of the governor of California drinking the water from our facility during a visit during one of his campaigns. So again, the keys to success here that are, I think these are applicable to anyone, even here in Spain, is that the project has to meet the ultimate goal. In our case, the goal is to find another source of water to replenish the groundwater, which is the main source of drinking water. That's what we were successful at. And then one of the things that allowed us, at least in our particular case, to be successful was we insisted on the highest quality. There were some regulations in place that would allow for us to not have to go through this level of treatment for certain portions of the water, especially the component of the water that we spread or surface spread or put in a spreading pond could have been treated to a lesser degree. But our board of directors decided at the time that we should treat all of the water, whether we inject it along the coast for seawater intrusion or surface spread it and take advantage of the treatment through the soil, we should still treat it to the highest quality. And that means putting it through microfiltration, reverse osmosis, and the advanced oxidation process. And then we had a history with our Water Factory 21 facility. So not only could we say that we think we could be successful in building a project like this, we had a track record or a history of operating a similar facility, although much smaller, for 25 years and not negatively impacting the groundwater. With that facility, we could show that we could be successful by making a larger project with a bigger reach. And so the outreach portion of it, as I mentioned before, is one of the key components, the continuous outreach. And one of the other message that has to be, at least in our case, that had to be implemented was the water doesn't directly go to consumers. At the end of the day, this project is what we call an indirect reuse project. So all the water that we produce ends up in the groundwater basin itself. It mixes with other naturally occurring water sources in the groundwater basin, as well as the other sources that we use to replenish the groundwater basin, including local river water and imported water. So once all of that water mixes together, it stays underground for more than 6 months most of the time before it ever reaches one of the production wells or a consumer's tap. So there is that, what we call that additional barrier buffer, what we call an environmental buffer. There's this, that's what makes the public feel a little bit more comfortable as well about the project, is that none of the water actually goes directly into the distribution to people's uses. It has to mix with the underground aquifer, be pumped out by some of these water retailers, and then it may or may not go through additional treatment at that time. Most of the time it doesn't, and then reach the consumers. And so because of that, we've been able to have a very successful project that we're still proud of today. And just to conclude, this is an aerial photograph of not only our facility, but at the top, that's the wastewater facility itself. So you can see that the kind of circular clarifiers at the top, that's the Orange County Sanitation District, and our facility is located along the bottom of the photograph at the bottom here, at the bottom border. We're located right next to each other. That's another reason that makes this project make a lot of sense, is that we're literally neighbors next door to each other. The water only has to travel a few thousand meters to reach us. We put it through our treatment, and then we can distribute it to our seawater intrusion barrier and pump it to our spreading basins. And so that close partnership not only is between the two public agencies, it's also because of our close proximity to each other. And that's something that, we didn't plan for. That was something that was started a long time ago before our facility, but that's what makes this project and this public partnership unique. Thank you.
Thank you.